Welcome to week 1 of Boltzmann Law, Physics to Computing. This is the 4th lecture. Now, as you may recall, in the first couple of lectures, we introduced this Boltzmann law for the equilibrium probabilities and also this concept of entropy. And in the last lecture, we obtained an expression for the entropy in terms of these probabilities. That is, we assumed a system that is occupied according to certain probabilities P, which are not necessarily the equilibrium ones. They could be, but not necessarily. And so we use the tilde to denote it, to give it a different symbol from the equilibrium ones. But we obtained a general expression that would work irrespective of whether it's equilibrium or non-equilibrium. Now, what we'll do in this lecture is we'll talk about this concept of free energy and use it to discuss some of these concepts of equilibrium and non-equilibrium and the distinction between them. Okay. Now, to start with, the first few slides, I guess we'll be doing a bit of algebra. We'll use these expressions that we obtained in the last lecture, remembering we have this system with certain energy levels E sub I and certain number of particles associated with each one of them, and this is all in state space, and each one is occupied with a certain probability which could be the equilibrium but need not be. And then we have this expression for entropy, for energy, and for the number of particles. And the free energy is defined as E minus mu n minus Ts. Now, first step is we take these expressions and substitute it back in here. So for example, when you have E, that's like Pi times Ei, and so we get this first term. Then N is Pi times Ni, and so that's how you get the second term. And S is Pi log Pi, that's how you get the third term. And of course, this minus k here and the minus t combine to give you a plus kt. Next, we pull the kt out of here and put it in front. So the Ei minus mu ni gets divided by kt. Now, next what we'll do is use this equilibrium probabilities to replace this term over here. So what we do is start from this expression, take the natural log of both sides. So log of Pi is equal to log of 1 over z, which is minus log z. And then the logarithm of e to the power minus x is just minus x. So that's how you get this term. So taking the natural log of this probabilities, we get this expression. And then if you rearrange it a little bit, you get this Ei minus mu ni over kt is equal to this quantity, which we can now substitute back in here. So instead of this quantity, we can put this n. And when we do that, we get, you see, there will be a Pi log z, and then there's a minus Pi log Pi, which is this second term. And you already had a Pi log Pi with the tilde before. So this term came from what was there before, whereas this term and this term came from these two. Okay? Okay. Now, next what we do is we note that this summation I over all P sub I, that's really constant. That's just 0. That's just 1, because all probabilities, equilibrium or otherwise, they must add up to 1. So I take that out. And so this term becomes minus kt log z. And then you have the logarithm of this Pi tilde minus logarithm of Pi. So you could write it as logarithm of Pi tilde divided by Pi. So that's this final expression for the free energy that we are trying to obtain. Now, you'll notice that if the probabilities of your system are actually equal to the equilibrium probabilities, then you see log of 1, which is 0, and so this term just drops out. And then you get a minus kt log c. That would be the f. Okay. Now, what's not so clear is that at equilibrium this is 0, but the point is when you are off equilibrium, so that these tilde pi's are a little different from the equilibrium ones. The point is that this quantity will always be positive. It will never be negative. Right? That's not an obvious thing. You can prove it mathematically, but what I'll do is just give you an example to show how this works. But the idea is then that the free energy is equal to minus kt log z plus a quantity that's always positive. And so at equilibrium, when the tilde pi's are equal to the equilibrium pi's, you get a minimum value for the free energy. And any other distribution will give you something bigger. Now, just a quick example I ran on MATLAB, you could do it also and check it out, is here's two examples. That supposing this is the equilibrium distribution, that you got 10 states, each has these probabilities, and this has certain probabilities. These tilde pi's are something different. It's not equal to the equilibrium ones, let's say. And they're both just selected at random. So what will happen is some of these will be bigger than the others, and some of them will be smaller. So if you look at the difference, some will be positive, some will be negative. But if you add them all up, it will be 0. Why? Because the sum of all the tilde pi's is equal to 1. Sum of all the equilibrium pi's is also equal to 1. So if you look at the difference and sum it, that must be 0, since the sum of each one is 1. And that's exactly what you'll find, that if you do that, you'll get a 0. But if you plot this quantity, pi log pi over pi, I mean the tilde pi over pi, then you will find that the positives are a little bigger than the negatives. And overall, it always comes out positive. This is something you could prove mathematically also. Right? This is known as the Gibbs inequality. And often in statistics, people use this to compare two distributions. That supposing I have a reference distribution, which is the pi, just like our equilibrium distribution, and you have some other distribution that you actually have, the non-equilibrium one, then how far one is from the other, there is one measure people use called the Kullback-Leibler divergence. And that's exactly this expression. And the point is, when the distributions match, you'll get 0. When the distributions don't match, you'll get some positive number. Okay. Now, the result is that, you see, when you're at equilibrium, then you see this thing goes out and f is equal to minus kt log z. And at that stage, if you change the probabilities a little bit so that the energies change, so that the total energy changes, or the number of particles changes, or the entropy changes, but the point is the f itself won't change because it's a minimum. So it is, no matter what you do, it kind of stays there and doesn't change much. At a minimum, as you know, a function has no change. The derivative is 0. And another way to look at it is when you look at the z, you see, because the probabilities must add up to 1, the z is like the sum of all these exponentials. And the individual probabilities can change, but this sum doesn't change to first order. And the result is that df is equal to 0 when you make small changes in your probabilities. And what that means is that when you look at when df is like dE minus mu dN minus TdS, because when I change these probabilities a little bit, energy will change, the number of particles will change, the entropy will change, so this will change, but overall this quantity cannot change, so it will be 0. And then with a little algebra, you can turn this around and write as ds equals dE over t minus mu over t dN. And this is the expression that I had stated before. If you remember that 1 over t was defined as the derivative of s with respect to E, and minus mu over t was the derivative of s with respect to n. And these are all these all hold only when you are really close to equilibrium. So these are relations that are true at equilibrium. But when you are away from equilibrium, then the free energy is something bigger, which is given by this quantity. And you can use all these expressions to find S, E, N away from equilibrium. But at equilibrium, these thermodynamic relations would be satisfied. Now, in the next few slides, what I'd like to explain is how, in general, a lot of this flow that we see in real systems, in physical systems, is driven by entropy. And this is kind of important because you see in physics, there are two big branches. One is mechanics and the other is thermodynamics. And they evolved separately. You see, mechanics started with Newton's laws, from observing the planetary motion, for example. Later, about a few hundred years later, came heat engines, and that's when the science of thermodynamics started. And people recognized that heat was a form of energy, but it was somewhat different. And mechanics is usually driven by force, but heat is often driven by this entropy. And what I'd like to give you is a few examples as to how these entropy-driven processes work. So the idea is, supposing I have a system which is away from equilibrium, and it is exchanging energy and particles with some reservoir which is close to equilibrium. Now, when this energy and particles are exchanged, the free energy change of the reservoir will be zero because it's close to equilibrium. But for the system, what will happen is the free energy will always go down because to start with, you're not at equilibrium, so F is minus kT log Z plus some positive quantity, and then as you get to equilibrium, this second term goes away and you get to minus kT log Z. So what that means is, of course, dF is dE minus mu dN minus TdS, and similarly dFr is d energy dE of the reservoir, dN of the reservoir, ds of the reservoir. And this one is equal to 0, but this one is less than or equal to 0. And so if you just, with a little algebra, if you turn it around, you'd see that the entropy change of the reservoir is equal to this, whereas the entropy change of the system is bigger than this. And it all follows because the system is not at equilibrium, whereas the reservoir was close to equilibrium. Now, of course, when it's exchanging energy and particle, the thing is, whatever energy you put into the system, you're taking from the reservoir. Similarly, the particles. What that means is that the change in the energy of the reservoir is the negative of the change in the energy of the system, because overall energy is conserved. So if dE is positive, then dE reservoir must be negative. Similarly, if dN is positive, dNr must be negative. So those two are related. So these ER and NR that are appearing on the right-hand side are related to the E and N on the left-hand side. So if I now add these two quantities, what will happen is dE over T will cancel dEr over T. Why? Because dE plus dEr is equal to 0. Similarly, dN and dNr will cancel. So overall then you get ds plus dsr must be greater than or equal to 0. Right? And that's the point I was trying to make, that usually, again, the flow will occur in such a way so that the overall entropy, the entropy of the system plus the entropy of the reservoir, will go up. And why is that? Well, again, because entropy is a measure of these number of states that are available. And so, generally speaking, all the flow will occur in such a way that things spread out in terms of all the available states. If your certain states are filled to start with, but then as you let it evolve, it will tend to fill up everything. And so that's why the entropy will increase. Now, if both sides are at equilibrium, then there could be energy exchange or particle exchange. But then, of course, on both sides we will have an equality, and as a result, there will be no change of entropy. There will be some exchange, but no real change of entropy. That's when both are at equilibrium. Now, one interesting condition is when both are in equilibrium, but with different temperatures. That's like one of them is hot and the other is cold, and we bring them together. The question is, which way will the energy flow and which way will the particles flow? Okay, so again we can write change in the entropy of the reservoir is this dE minus mu dN over T, same here, and both are actually locally in equilibrium, so both we have this equality here. So if it was out of equilibrium, then we'd have the greater than or equal to, but in this case it's equal on both sides. Okay, and then of course energy conservation, so change in energy of the reservoir is negative of the change of energy of the system. Change of energy of particles in the reservoir is negative of the change in particles of the system. Now let's add the two. So when I add these two, then what I get is dE times 1 over T1 minus 1 over T2, 1 over T. Because we get the 1 over T1 from here and 1 over T from here. And the minus sign, well, because dER is negative of dE. Similarly, dNR is negative of dN, so you get minus mu n also is multiplied by the same factor. So this is now the change in the overall entropy. Now the question is, which way will the energy flow? What will be this dE minus mu n? And the answer is, well, you see, if say this side is hot and this side is cold, what it means is T1 is large compared to T. So if T1 is large, that means this 1 over T1 is small compared to 1 over T, and so this quantity is negative. And overall the entropy change must be positive, and so this quantity must be negative. So the flow will occur in such a way that dE minus mu n is less than 0. So what does that tell us about heat flow? Well, supposing the system and the reservoir are only exchanging energy but not particles, so dN is 0. Then what this tells us is that dE must be less than 0. Well, dE less than 0 means, the way we have chosen the direction of E, it's flowing from the reservoir to the system. So if it is less than 0, it means energy will be flowing from the system to the reservoir. In other words, heat will be flowing from hot to cold, which is exactly what we know would happen. Heat always flows from hot to cold, but what we showed here is how that follows from the principle of increasing entropy. What if electrons are exchanged as well? Well, then you see when an electron comes from one side to another, the number of particles is changing, there's a dN, but there's also an associated change in energy, which is epsilon times dN, if each electron or particle carries this energy epsilon. So dE minus mu n now looks like epsilon minus mu times dN. Now that quantity must be less than 0. So which way will the particles flow? Well, it now depends on whether you're talking of energy levels above mu or below mu. Because if you're above mu, then you see epsilon minus mu is a positive quantity, and then dN must be negative. What that means is that the flow must be from system to reservoir, will flow from hot to cold. On the other hand, if you look below mu, then epsilon minus mu is negative, and so dN must be positive. And that means they will flow from cold to hot. So in other words, for energy levels above mu, electrons will flow from hot to cold. Below mu, they will flow from cold to hot. And this is actually a very well-known phenomenon called thermoelectricity. That there are two types of solids. One's where N-type, where there are more states above mu than below, and so when you put a hot probe and a cold probe, the electrons flow, the net flow is from hot to cold. And there are P-types where there are more states below mu than above, and in that case it flows the other way. Once again, a well-known phenomena, but what we're trying to show here is that everything follows from this principle of increasing entropy, which is what is known as the second law of thermodynamics. You see, everybody recognizes the first law of thermodynamics, which is that energy is conserved. What the second law says is, yes, energy is conserved, but it spreads out over all the available states. So if it is originally in one particular state, it will gradually want to spread out over everything that is available to it. Well, that kind of summarizes or finishes up what we wanted to talk about of these general principles of statistical mechanics, of this Boltzmann law. And in this lecture, we talked about the concept of free energy and this relation between equilibrium and non-equilibrium. And earlier, we had introduced this concept of entropy. Now, what we'll be doing in the next lecture is something different, which will lead into the rest of the course, where we'll be talking about neural networks and quantum computing. And what we'll be talking about is this notion of a self-consistent field. You see, the state space, as I've mentioned, has 2 to the power n states, which is huge. And in general, whenever you're trying to compute something, one of the difficulties is that this is such a huge space. Now, there is this method that is widely used, which allows you to do your calculations in this other space, the space of n states. Remember, we started from these n levels. We talked about how the state space had 2 to the power n levels. So what we'll describe in the next lecture is this method which provides a practical approach for dealing with large interacting systems. Thank you.